Look up. Beyond the clouds, past the thin blue veil of our atmosphere, lies a vacuum of unimaginable scale. For millennia, humanity has gazed upon this frontier, dreaming of ascending. But what if the ultimate journey to the stars began not with a fiery rocket blast, but with a humble, ancient impulse, the urge to simply climb? The space elevator, often dismissed as a fanciful dream from science fiction novels, is in truth something far older, far more deeply ingrained in our very nature. It is the logical, perhaps inevitable, endpoint of a 10,000-year-old human quest to connect worlds, to conquer the vertical challenge that has always defined our limitations. From the very first rough-hewn ladder leaning against a tree, we have sought to ascend, to bridge the divide between what is here and what is above. Consider the breathtaking ingenuity of the ancient Incans, who, in the treacherous vertical world of the Andes, wove together gravity-defying rope bridges spanning impossible ravines. These were not mere transport links. They were arteries of empire, conduits for vital communication, and powerful symbols of social cohesion, uniting disparate communities across terrain that would otherwise be impassable. The delicate balance and engineered strength of these swaying structures, some extending for dozens of meters across chasms thousands of feet deep, offer a surprising parallel to the envisioned orbital tether, a structure that must defy gravity on a scale exponentially grander. And what drove the creation of ancient superhighways like the fabled Silk Road, a network of trade routes stretching for thousands of kilometers from China to the Mediterranean, or the equally vital Amber Road that snaked across ancient Europe? It was the insatiable human desire for high-value, low-mass goods, exquisite silks, exotic spices, precious amber, items that justified the immense cost and peril of overland travel across vast, unforgiving landscapes. This very same economic principle echoes powerfully in our modern era, driving the relentless demand for swift satellite deployment into orbit or the speculative, yet tantalizing, promise of resources mined from distant asteroids. The value of placing critical infrastructure in space is immense, the mass comparatively tiny, and the primary barrier to access remains Earth's powerful gravitational well. Delve deeper into our collective psyche, and you will find the pervasive myth of the Tower of Babel, humanity's audacious attempt to build a structure that reached the heavens, a monument born of a primal urge to transcend earthly bounds. This ancient psychological narrative finds an uncanny resonance in the engineering dreams of Konstantin Tsiolkovsky, a quiet Russian schoolteacher who, in the year 1895, long before the frantic scramble of the space race, first articulated the concept of a celestial castle, an orbital structure connected to Earth by an impossibly long cable. Tsiolkovsky, working in relative obscurity, saw beyond the limitations of rockets, envisioning a permanent, far more efficient pathway to the cosmos. Fast forward to the Cold War, a period defined by the fierce competitive race to the moon. While the American Apollo program captured the world's imagination with its thunderous rocket launches and dramatic lunar landings, recently declassified Soviet-era technical papers reveal a parallel, often forgotten, line of inquiry. Soviet engineers and scientists were seriously considering early, non-rocket space launch concepts, not merely as a tactical countermeasure in a technological arms race, but as a calculated, long-term economic investment. They understood that the true prize wasn't just reaching orbit once, but establishing an enduring, cost-effective infrastructure for the sustained utilization of space, a vision far grander than simply planting a flag or winning a momentary sprint. This, then, is the profound insight at the heart of the space elevator concept. It is not a radical new invention, not merely a futuristic fantasy, but rather the ultimate, grand expression of our species' innate, persistent drive to construct infrastructures that fundamentally compress space, time, and cost. It promises to transform the vast, seemingly impenetrable sky from an insurmountable barrier into an accessible, everyday highway. To truly grasp its potentially transformative power, we must look not just at advanced materials or orbital mechanics, but back through the annals of human history. Reflect on the monumental socio-economic impact of the sprawling network of Roman roads, which did not just facilitate travel, but forged an empire, united diverse peoples, and enabled unprecedented trade across a continent. Or consider the intricate web of the British railway system, which fueled the Industrial Revolution, connected distant cities, and reshaped nations. These were not merely engineering marvels. They were catalysts that unlocked unprecedented economic potential, facilitated the rapid flow of goods and ideas, and fundamentally redefined human civilization. The space elevator, viewed through this deep-rooted historical and anthropological lens, promises a similar, if not infinitely greater, paradigm shift, offering a permanent link to orbit that could redefine humanity's relationship with the cosmos itself. For centuries, across darkened laboratories and through the whispered dreams of alchemists, humanity has pursued the elusive, the impossible. Not gold from lead, but materials that defy our current understanding, substances that promise to unlock new realities. The quest for the philosopher's stone, the mythical substance capable of transmuting base metals, finds a surprisingly direct echo in modern material science, particularly when we contemplate the gargantuan challenge of building a road to the stars. The space elevator, often simplified to the need for just stronger carbon nanotubes, demands a deeper investigation into how the seemingly unattainable can, through ingenuity and perseverance, become utterly commonplace. Consider the forgotten story of a material once so precious, so rare, that it commanded a price higher than gold itself: aluminum. In the mid-19th century, this silvery white metal was a symbol of ultimate luxury and technological prowess. Napoleon III, so enamored with its rarity, reserved aluminum cutlery for his most honored guests, while lesser dignitaries were relegated to mere gold. In 1884, a shining capstone of pure aluminum, weighing 100 ounces, approximately 2.8 kilograms, was placed atop the newly completed Washington Monument, a testament not just to American ambition, but to the extraordinary value of this exotic element. Yet, within just a few short decades, aluminum transitioned from a king's treasure to the disposable wrapper on your candy bar. This radical transformation was not due to a sudden discovery of vast natural reserves, but to a profound leap in industrial chemistry. In 1886, almost simultaneously, two brilliant minds working independently, Charles Martin Hall in America and Paul Héroult in France, developed the electrolytic process that forever changed the economics of aluminum production. By passing an electric current through molten alumina dissolved in cryolite, they unlocked a method for extracting the metal cheaply and at scale. This pivotal moment serves as a powerful historical case study, a blueprint for understanding the formidable journey that any material, however revolutionary, must undertake to move from laboratory curiosity to industrial-scale production. Today, the materials envisioned for a space elevator tether, such as lab-grown diamond nanothreads or flawless graphene ribbons, stand at a similar precipice. They possess theoretical tensile strengths far beyond anything we currently manufacture, hundreds of times stronger than steel. Yet their production remains largely confined to controlled laboratory environments, measured in mere grams or microscopic flakes. The path from a few milligrams of an exotic compound to a continuous ribbon stretching nearly 100,000 kilometers, or 62,000 miles, is not merely one of scaling up, it is an economic and engineering odyssey fraught with challenges. Across the globe, in cutting-edge research facilities from Japan to China, scientists are already pushing the boundaries of continuous carbon fiber structures. Their focus isn't explicitly on space elevators, but on next-generation energy storage, lighter aerospace components, and advanced industrial applications. Researchers are achieving kilometer-scale carbon fiber lengths, demonstrating the feasibility of long-form material synthesis. This ongoing research, driven by diverse commercial and scientific imperatives, quietly lays the groundwork for the colossal task of manufacturing a tether that could withstand the immense stresses of Earth's gravity and the unforgiving vacuum of space. This brings us to the concept of material economics. The primary obstacle to realizing the space elevator isn't just achieving a certain tensile strength, a single number on a specification sheet. It's the intricate dance of energy cost during production, the excruciatingly low defect rate required for a structure of such critical importance, and, perhaps most dauntingly, the sheer scalability of manufacturing. These are precisely the same formidable problems that confronted the pioneers of steel production in the Industrial Revolution, or the architects of the Silicon Age, who transformed a common element into the bedrock of our digital world. The question is not just, can we make it strong enough, but can we make enough of it, without flaws, at a price that makes the entire endeavor economically viable. Beyond the purely synthetic, a fascinating biological parallel offers a completely different, perhaps more sustainable, pathway. Consider the humble spider, master architect of nature's strongest known biological material, spider silk. Pound for pound, certain spider silks are stronger than steel, more elastic than nylon, and possess an astonishing self-repairing nature, characteristics vital for a colossal space tether. Institutions like the Fraunhofer Institute in Germany are at the forefront of biomimicry research, reverse engineering the genetic secrets of spider silk production, exploring how we might harness biological processes to grow, rather than forge, the materials of our future. This bio-inspired approach could lead to a manufacturing process that is far less energy-intensive and produces fewer defects, moving us towards a future where the strongest materials are not engineered with brute force, but coaxed into existence with biological elegance. For decades, the grand vision of a space elevator has captivated dreamers and engineers alike. Most imagine its greatest threats as obvious: a rogue piece of space debris, a stray meteorite, or perhaps a catastrophic material failure. But the true peril, the silent, relentless challenge that could unravel this colossal dream, lies not in the visible, but in the unseen forces that constantly buffet our planet and its surroundings. These are the subtle, complex geophysical and orbital dynamic forces that threaten the very stability of a tether stretching 100,000 kilometers into the cosmos. To grasp the magnitude of these hidden dangers, cease to see the space elevator as a static, immovable rope. Instead, envision it as the longest, thinnest guitar string in our entire solar system. This isn't just a poetic analogy, it is a profound engineering reality. Just like a guitar string, this immense tether would be susceptible to a symphony of vibrations, a relentless chorus of resonances that could amplify, building to destructive crescendos capable of snapping the ribbon. The challenge then becomes not just building it, but teaching this cosmic string to stay still. Meticulous modeling work, often conducted far from public view in specialized academic circles, has illuminated these hidden stresses. American physicist Bradley C. Edwards, in a groundbreaking 2003 study for the NASA Institute for Advanced Concepts, painstakingly identified one of the primary sources of these potentially catastrophic resonant oscillations: the gravitational tides exerted by both our moon and the distant sun. These are not just the ocean tides we see, but immense invisible forces stretching and compressing the entire planet, and by extension, anything anchored to it, causing the 100,000-kilometer tether to sway with a potentially deadly rhythm. Then there is the Earth's relentless spin. This rotation, a constant, fundamental force of our existence, gives rise to a truly immense and counterintuitive challenge: the Coriolis effect. It is a twisting force, an invisible hand constantly trying to spiral the ribbon and any climber ascending it. Imagine a colossal, invisible ringer, ceaselessly trying to twist this slender structure. This continuous torque would demand incredibly complex active stabilization systems, an intricate ballet of counterforces and adjustments, to prevent the elevator from coiling in on itself, or worse, tearing itself apart under the strain of its own movement. Even the air we breathe, thin as it becomes in the upper reaches of our atmosphere, holds surprising perils for the elevator. Delve into the realm of high-altitude atmospheric physics, and you discover phenomena like stratospheric lightning, electrical discharges far more powerful and energetic than typical thunderstorms, occurring high above the clouds. Pair this with the intense, hypersonic jet streams that surge through the upper mesosphere, and you have a recipe for destructive vibrations or even electrochemical degradation of the delicate ribbon material. These are not minor gusts of wind. They are supersonic currents of charged particles and immense electrical discharges, capable of relentlessly eroding or violently shaking the tether. And finally, the anchor point itself, the very ground from which this cosmic highway would emerge, presents its own set of profound geophysical challenges. Even minor seismic activity, a barely perceptible tremor in the Earth's crust, could be amplified along the astonishing 100,000-kilometer length of the tether, turning a tiny ripple into a devastating wave. Furthermore, our planet itself is not a perfectly stable top. It undergoes a slight, irregular movement of its poles known as the Chandler wobble. This subtle, almost imperceptible lurching of the Earth's axis, a natural planetary gyration, could also induce immense amplified stresses along the tether, posing an engineering challenge that is rarely discussed outside of the most specialized and advanced scientific forums. What if the greatest barrier to humanity's cosmic future isn't the vastness of space or the unforgiving vacuum, but something far more pervasive and insidious, something we feel every moment of every day, Earth's own immense gravitational pull? For centuries, our efforts to break free of this planet have been an endless battle against this invisible force. We pour colossal amounts of energy into launching rockets, each one a fleeting, violent struggle against the very ground beneath our feet. This perpetual fight, this astronomical energy expenditure, imposes an enormous, unavoidable cost on every ounce of material we send skyward. It is, in essence, the gravity tax, a crippling levy that dictates the entire architecture of our current space exploration endeavors, making every single launch an exercise in extravagant defiance. This relentless gravity tax has shaped our technological ambitions, limiting us to compact, lightweight payloads and the most valuable scientific instruments. But consider a future where this tax is fundamentally repealed. A space elevator, stretching 100,000 kilometers into geosynchronous orbit, promises to revolutionize this equation, transforming the vertical climb from an explosive sprint into a smooth, silent ascent. It would be a permanent, fixed infrastructure, enabling payloads to be lifted incrementally, slowly, and with dramatically reduced energy costs compared to the fiery fury of chemical rockets. The economic implications ripple out far beyond simply making space launch cheaper. They suggest a complete rewiring of the solar system's economy. The concept moves far beyond a mere transport system, evolving into the very backbone of a new cislunar industrial ecosystem. Take, for instance, the detailed economic and architectural plans proposed by Japan's Obayashi Corporation. Their 2012 concept wasn't just a theoretical musing, it was an intricately detailed blueprint, outlining how an elevator could anchor a vast network of orbital infrastructure. They envisioned it not merely as a way to get off Earth, but as the central artery for an orbital economy, a permanent sky bridge facilitating commerce, manufacturing, and even human habitation in Earth's immediate cosmic vicinity. It transforms the desolate vacuum above into an accessible, invaluable extension of our industrial capabilities, shifting our perspective from temporary expeditions to permanent residency. This new infrastructure would unlock possibilities that have long languished in the realm of science fiction due to prohibitive costs. Recall the visionary ideas of American physicist Gerard K. O'Neill from the 1970s, particularly his groundbreaking concept of space-based solar power. O'Neill proposed building colossal solar arrays in orbit, kilometers across, capable of beaming clean, limitless energy back to Earth. The challenge, then as now, was not the physics, but the economics. How do you lift the unimaginable volume of materials required to construct such gargantuan structures into orbit? With rockets, the cost remains astronomical, rendering such projects economically unfeasible. An elevator, however, would allow massive solar arrays to be constructed in orbit from terrestrial materials, transported steadily and affordably, making O'Neill's decades-old dream economically viable for the very first time. To truly grasp the transformative power of such a permanent link, we must look back to monumental shifts in terrestrial infrastructure. Consider the Transcontinental Railroad in the United States, completed in 1869. This wasn't just a faster way to travel from east to west. This iron spine, stretching over 3,000 kilometers across a vast wilderness, actively created new towns, spurred the growth of entirely new industries like cattle ranching and timber, and unlocked the economic value of previously inaccessible territories. It didn't just connect existing points, it forged new economic realities, reshaping the very geography of a nation. The space elevator promises a similar, if not infinitely greater, catalytic effect, not just connecting Earth to orbit, but creating an entirely new economic frontier, a cosmic extension of our global marketplace. Such an elevator would fundamentally alter the calculus for accessing and utilizing resources from beyond Earth. Asteroid mining, for example, often dismissed as a far-off dream, could transition from a speculative venture into a practical, industrial reality. The current challenge isn't just reaching an asteroid, it's the prohibitive cost of bringing refined materials, whether precious metals or volatile ice, back to Earth or into high orbit for manufacturing. The energy penalty of a planetary descent, followed by the need for a costly relaunch into orbit, makes most asteroid ventures uneconomical. However, with an elevator, refined materials from asteroids could be returned directly to high orbital manufacturing facilities without ever needing to contend with Earth's gravity well. This effectively turns the solar system's abundant resources inward, making them available for orbital construction, fueling space-based industries, and fundamentally shifting the very supply chains of the cosmos. The ascent to orbit. For decades, this phrase has conjured images of fire, thunder, and raw, unrestrained power. It is the roar of 1,000,000 pounds of thrust, the violent shaking of the ground, the blinding flash that tears through the sky. This is our inherited vision of space travel, forged in the crucible of the Cold War and epitomized by the heroic, perilous missions of Apollo. It is a spectacle of defiance against gravity, an act of sheer will that has embedded itself deep within our collective psyche as the only true way to leave Earth. But what if the greatest barrier to humanity's cosmic future is not a lack of advanced materials or insurmountable engineering challenges, but something far more subtle, a deeply ingrained psychological resistance to change? For if the space elevator ever becomes a reality, it will not arrive with the dramatic fury of a rocket launch. Instead, it promises a journey of profound stillness, a slow, almost mundane ascent, transforming space from a distant realm of conquest into a surprisingly accessible place of commute. Instead of being strapped into a colossal machine designed to escape Earth's gravity in mere minutes, passengers would embark on a quiet electric climb, perhaps taking several days to reach geostationary orbit, some 35,786 kilometers, or 22,236 miles above the equator. This radical shift from explosive heroism to silent transit challenges our fundamental understanding of what it means to travel to the stars. History offers powerful echoes of such profound technological and cultural shifts. Consider the public's initial reaction to the advent of the steamship in the early 1800s. For centuries, the majestic sailing ship, with its billowing canvas and graceful dance with the wind, symbolized freedom, skill, and adventure. These were vessels that harnessed nature's raw power, demanding the expertise of seasoned sailors who could read the currents and winds like a second language. Then came the steamship, an ugly, soulless contraption of iron and smoke, dependent on a rigid schedule and the constant feeding of its ravenous boilers. It was seen by many as a lesser, almost vulgar alternative, an affront to the romance of the open sea, despite its undeniable efficiency and reliability. A similar transformation occurred with the arrival of the railway. For generations, personal freedom on horseback or in a carriage defined overland travel, offering spontaneous detours and the inherent unpredictability of the open road. The railway, in stark contrast, imposed a rigid schedule, confining travelers to a fixed track, shuttling them along at previously unimaginable speeds, but stripping away the personal agency and the immediate connection to the landscape. It replaced the individual's journey with a collective, mechanized transit, a change that felt anticlimactic to many who cherished the independence of the road. The space elevator presents an analogous leap, demanding a similar re-evaluation of our deeply held romantic ideals of exploration and journey. Cultural sociologists and cognitive psychologists have long explored what they term the psychology of the sublime, the overwhelming sense of awe and wonder evoked by phenomena of immense power and scale. A rocket launch, with its sheer kinetic energy, its deafening roar, and the raw, elemental display of fire and smoke, taps directly into this primal human capacity for awe. The spectacle itself is transformative, a visceral experience that few other human endeavors can replicate. A silent electric climber, patiently ascending a thin ribbon towards the heavens, while a marvel of engineering inherently lacks this explosive, sublime power. It simply cannot ignite the same emotional spark, the same feeling of heroic conquest that has defined our space age. This absence of dramatic spectacle could, paradoxically, create a significant cultural resistance. Humanity has woven archetypal stories of exploration and heroism around the fiery chariot, the daring leap into the unknown. Our narratives of space travel are intrinsically linked to risk, bravery, and the thunderous overcoming of physical barriers. The space elevator, by offering a journey that is safe, slow, and predictable, fundamentally challenges these ingrained narratives. It feels, to some extent, anticlimactic. If we are to truly embrace this quiet path to the stars, we need more than just a monumental engineering revolution. We require a profound storytelling revolution. New narratives must emerge, new myths forged, that frame this novel form of cosmic travel not as a lesser, less heroic alternative to rockets, but as a sign of a more mature, more sustainable, and ultimately more integrated relationship with the vast cosmos. It is a shift from conquering space to coexisting with it, from an explosive departure to a quiet, considered extension of our earthly presence. The question then becomes not just if we can build it, but if we can truly, psychologically, accept it. What if the ultimate prize in human history was not a continent, a vast ocean, or a hidden vein of gold, but a single, solitary pathway? A thread connecting Earth to the stars. The space elevator, often considered a feat of engineering or a scientific enigma, is in truth a crucible for the most intense geopolitical storm humanity has ever faced. For whoever controls this slender road to orbit would command a concentration of power far exceeding any strategic choke point in our past. Consider the Suez Canal, a man-made marvel that dramatically reshaped global trade, shortening voyages by thousands of kilometers and connecting East and West with unprecedented efficiency. Or the Panama Canal, a triumph of engineering that bridged two vast oceans, allowing ships to bypass the perilous journey around Cape Horn. Both are arteries of immense global commerce, wielding significant geopolitical influence. Yet, a single space elevator, anchored within the borders of one nation, would grant its owner dominion over access to the cosmos itself, a power far beyond the terrestrial. It would effectively be the new Gibraltar, not just controlling maritime passage, but dictating who ascends to the heavens and who remains bound to Earth. The international framework designed to manage space, the 1967 Outer Space Treaty, stands as a stark relic of a bygone era. Forged in the nascent years of the space race, when exploration was largely the domain of national governments and temporary expeditions, this treaty is glaringly inadequate for the permanent, privately or nationally owned, orbital infrastructure a space elevator represents. It speaks of common heritage and non-appropriation, but offers no clear guidelines for owning, operating, or regulating a structure that literally reaches from one nation's soil to a fixed point in geosynchronous orbit, some 35,786 kilometers above the equator. This fundamental legal void invites a dangerous future. A game theory simulation of the likely political fallout paints a sobering picture. The potential for economic blockades, where access to space is denied to rival nations, could cripple emergent space-based industries and surveillance capabilities. The anchor station, a colossal facility housing the base of the elevator, would become the single most valuable strategic target on the planet, inviting military threats and the specter of a new, orbital Cold War. Nations would scramble for control, not just for economic advantage, but for the inherent military dominance that unrestricted access to orbit provides. It is a terrifying prospect, transforming the peaceful frontier of space into the next battleground for global supremacy. The search for suitable governance models becomes paramount. One proposal suggests a United Nations-administered international zone, akin to the Antarctic Treaty System, where a continent is preserved for scientific research and international cooperation, free from national claims. This would ensure equitable access and prevent a single entity from monopolizing the space highway. Another model, perhaps more pragmatic given humanity's commercial impulses, envisions a corporate consortium similar to the powerful entities that manage the vast network of transatlantic internet cables. These private entities, driven by profit and shared interest, successfully govern crucial global infrastructure. But could such a model truly withstand the immense geopolitical pressures of controlling the gateway to space? Furthermore, we must confront the chilling military implications. Declassified Cold War-era studies, once confined to the shadowed halls of strategic planning, explored the weaponization of orbital tethers, not necessarily the elevator itself, but similar long structures in space. A space elevator, by its very nature, could be seen as both an irresistible target for rivals and an unparalleled platform for strategic assets. Imagine launching surveillance satellites, hypersonic delivery systems, or even orbital defense mechanisms directly and affordably from its apex. This forces a complete and urgent rethinking of national security, transforming the very definition of a nation's defensive perimeter. The central, unavoidable question then becomes, are our current international political structures, forged in an age of terrestrial disputes and defined by national sovereignty, mature enough to manage a project that is, by its very nature, both global in its impact and yet singular in its physical, monumental location? For centuries, humanity has gazed upon the concept of a space elevator, often weighing it against a simple question: is it real, or is it merely a fantastical dream? We have meticulously dissected its engineering complexities, debated the exotic materials required, modeled the unseen cosmic forces that would challenge its stability, analyzed its profound economic implications, confronted the psychological shifts it demands, and even grappled with the intense geopolitical storms it would unleash. Yet, as we draw this cosmic narrative to a close, it becomes clear that the space elevator is far more than a mere engineering conundrum. It stands as a profound litmus test for our species' very maturity, a mirror reflecting our capacity for cooperation and collective vision. Consider this: building such a monumental structure, a tether stretching 100,000 kilometers into the void, would be an act of transforming our planet itself into a new kind of symbiotic organism. Earth, currently bound by its gravitational embrace, would extend a permanent appendage, much like a plant sending out a root to draw nourishment, or a tendril reaching for light. This is not just a poetic flourish. It suggests a fundamental biological and technological integration, a conscious act of planetary-scale biological extension. It echoes the profound insights of the Gaia hypothesis, first proposed by groundbreaking scientists James Lovelock and Lynn Margulis in the 1970s. They posited that Earth and its living inhabitants function as a single, self-regulating system. A space elevator, in this context, would be humanity's deliberate contribution to Gaia's extended form, a purposeful limb reaching out to interact directly with its cosmic environment. The true barrier to this astounding feat is not, as many might intuitively believe, a lack of a specific miracle material, nor an insurmountable technological hurdle that lies perpetually beyond our grasp. The most formidable obstacle, the one that has historically fragmented our greatest ambitions, lies deep within our own nature, our propensity for division, our competitive instincts, and our often crippling inability to unite for a singular, monumental purpose. It is the human element, the political will, and the shared commitment that will ultimately determine if this audacious vision can ascend from blueprints to reality. Yet, even if the monolithic dream of a single, colossal space elevator seems too daunting for our fractured world, the pathway to the stars may still begin with smaller, more incremental steps. We look to less demanding, yet equally innovative, alternatives that could serve as crucial stepping stones. Consider the spaceline concept, proposed in 2019 by Zephyr Penoyer and Emily Sanford. This brilliant idea envisions a tether extending not down from Earth, but up from our moon. Anchored to the lunar surface, its lower gravity and lack of atmosphere dramatically simplify the material and engineering challenges, potentially offering a more attainable first cosmic foothold, a quieter, less contested route into the solar system. So, as we contemplate this extraordinary road to the stars, stretching from our terrestrial home to the distant realms of orbit, we are left with a question that transcends mere physics or engineering. Is the space elevator a mere fantastical dream, a relic of ambitious science fiction? Or is it, in fact, an evolutionary necessity, a tool we must collectively forge to ensure our long-term survival and to shepherd humanity's profound transition from a purely planetary species to a truly multiplanetary future?